Okay, here we go. So part 2 of ABCs of comfort. I actually didn't have this particular slide originally in my presentation, but I happened to find it online the other day. Somebody sent it to me. It's an old ad from the Buffalo Forge Company, which is actually where Willis Carrier got his start. But it kind of pointed out some of the exact things we were talking about last week in terms of comfort, right? So temperature and humidity and air motion are 3 things we focused on quite a bit. We also talked a lot about radiant temperature as well, and we mentioned other stuff like indoor air quality and acoustics and those sorts of things. So I thought it was kind of funny. I saw this ad from 1935, and it's pretty much the same stuff then is what makes people comfortable now, although expectations of the occupants are a little more accelerated nowadays than they were then. So we're continuing on with our discussion here, tying some of those comfort aspects that we talked about into actual mechanical systems. For some of you that have been around a while, the next 5 minutes will be a little bit remedial, but we'll get into more interesting things as it progresses here. So we got lots of components that are involved. Like we said, we have there are 4 main heat transfer types that we're dealing with: convection, conduction, radiation, and evaporation. And now I'm going to use mechanical systems to aid in those heat transfer mechanisms to speed them up, or in some cases slow them down for me. So our basic system, if we look at it, basically a simple residential system for right now, just to kind of put it in perspective, because everybody has a residential system at their house, and the same principles apply to commercial systems as well. So first off, I need some sort of air handling device. In this example, it's number 1 on the drawing. It's a furnace. It could be a fan coil. It could be an air handler. It could be anything basically that has a blower on it to move air and distribute air. I need an evaporator coil for the refrigeration process. That's number 2 on the drawing here. So this coil is 1/2 of my surface area for my air conditioning system. The other half is outside, number 5, the condensing unit. And we'll talk about some of these pieces as we go, and what's inside the condensing unit and what's inside the evaporator coil. But I need the condensing unit paired up with the evaporator coil in order to move heat from my duct system and reject it to the outdoors. I may or may not have a humidifier. Residentially in older homes, it's very common. Commercially, it's only common in specialty applications like libraries and daycares and hospitals and stuff like that. I have some type of filtration device that I need to protect the equipment. In this example, they're showing an electronic air cleaner. It's more likely going to be a media filter, or it could be even an air purifier. That guy's there primarily to keep junk off of our coils. We don't want dirt building up on our heat exchanger in the furnace, nor do we want it building up on our evaporator coil. So that filter is there to catch those items so they don't get on those surface areas and reduce our heat transfer. Nowadays, it's also common to have beefed up filtration devices to also filter finer particles out of the air to help protect the building occupants. Number 6 down in the drawing in the bottom right hand corner there is a ERV. These are not super common residentially in our climate, just because we don't have the whole run hour versus first cost type argument. Commercially, it's becoming more and more common, and some of you guys have been on the ERV webinars commercially that we've done. We've talked about when it's required by code and it's rebatable from utilities and that kind of thing. But residentially, it's not super common. But in either case, what that guy's job in life is I'll see if I can use my little pointer thing here. He takes air from, in this example, it's pulling it out of the return duct, although it's more common to pull it out of the bathrooms and other exhaust sources. We run that air through the ERV, or HRV in this case, and that guy saves the energy from that air. So he saves his heating energy, his cooling energy, his humidification or his dehumidification energy, and then takes the dirty air molecules and dumps them to the outside, out that path, out the outside wall. Then we take in on the other side of the heat exchanger in the ERV, we suck in fresh air from outside, we run it through that same heat exchanger and pick up all of that cooling and heating energy that we just left there and bring that back into our system. So it is a pretty good energy saving device in terms of bringing more fresh air in without having to pay a bunch of energy to heat it and cool it. We have to have some type of air distribution system. There are systems that are not ducted, right? So radiant floors, for example, radiators, fan coils, variable refrigerant flow, duct-free splits. But much of what we do residentially and commercially is ducted systems. That's the most common scenario in the United States. So we need some sort of ducting system. Typically that consists of a few main components. One is the supply duct. So the air that goes through the filter, furnace, and evaporator then goes into the supply duct where it's distributed around the building, in this case a house, and then comes out the supply diffusers, oftentimes residentially referred to as registers or grills. If we're going to shove air into a room, we have to have a way to get the air back out of the room, right? I can't keep blowing air into a balloon and not expect the balloon to blow up if I don't have a way for the air to get back out the other side. So in order to get the air out of the room, I have to have a return ducting system. That consists of the return grills. They can either be mounted on the floor like they are in the drawing here, or they could be mounted up on the high wall in some cases. They pull air from the room and bring it back to the system to run it through the filter, furnace, and evaporator coil and redistribute it again. Right? So I need to put air into the room and I need to pull it out. However much air I put into the room, I need to basically pull the same amount of air out. So if I'm going to throw whatever 100 CFM into a particular room, I have to have a way for 100 CFM to get back out of that room. Now in a lot of cases we will slightly pressurize buildings. That way we have some slight exfiltration through the building envelope instead of infiltration, but it's a very small percent. So in my example, if I put 100 CFM into a room, I probably need to be able to get 90 CFM back out of the room through the return duct system. If you have rooms that don't have a return duct, it's going to be very hard to condition those rooms unless you leave the room's doors open, which in most cases, like a bedroom, you don't want to do. I need to have some devices in this building to control all of that. Our normal control device, number 9 in the drawing here, is a thermostat. That's the most common scenario. He basically knows what temperature you like and what temperature it is, and he decides if he should put on heating or cooling or neither in order to give you the comfort that you need. And then as systems get more complicated, instead of just turning on heating and cooling, he may have multiple stages that he needs to stage up, or he may have modulation capacity with inverter compressors and modulating gas valves and stuff like that. In some cases, there will also be humidity sensors built into that thermostat to make sure that we don't go too high or too low on the humidity. So those are kind of our basic overall components in a house or in a light commercial facility. They don't always look the same. Sometimes things are different, right? Maybe you don't have a furnace, maybe you have a fan coil because you don't have a gas system, things like that. But those are kind of our basic components, and we're going to go into some more detail on some of these components here. So, on the air side of the system, if I only was concerned with your body heat and there was nothing else that generated heat, then I basically could put a fan in this room and just suck air out of the room and pull your body heat away with it, and new air would come back into the room, and that would be sufficient. Unfortunately, that's not the case. My building envelope itself is losing or gaining heat depending on the weather outside. Plus, I may have other stuff in the building that causes heat gain. So a fan is really only going to be one piece of this overall pie. So in order to decide what I need to do in terms of heating and cooling equipment and types, I need to first figure out how much heating and cooling I'm going to need. So we have different types of heat gains and heat losses for the building. Right now we're showing internal heat gains. So that is where the building is picking up heat from, other than the boiler or furnace, obviously. But where else is it getting heat from? And that heat I might have to remove, especially in the summertime. So first off is the people. We already talked about that a lot last week. People generate quite a bit of heat, and we need to remove that heat from the space if we're going to try to cool this space down. The lighting also could be a fairly large source of heat energy. More modern LED bulbs give off very little heat, but older technology that you find in lots of buildings and lots of houses with incandescent bulbs and stuff like that give off a ton of waste heat, and we need to take that into account when we're removing the heat. And similarly, if I know the building is going to be designed with LEDs or redesigned with LEDs, I need to take that into account because the size of the system I thought I needed is going to be smaller for the cooling system than I originally planned. In some places, in industrial facilities and manufacturing facilities, I might have other stuff like motors, or if it's a kitchen, appliances, fryers, and all that kind of stuff that I might have to deal with. Like we said, for purposes of this class, we're sticking on occupant-based buildings, so we're not going to talk about kitchens or manufacturing areas or process plants. We're going to stick with the people and lights and external gains. Our external gains are the heat that we're picking up from the outdoors. There are 3 main ways that heat is going to make its way from outside to inside our building. And all that heat that makes its way in, I've got to find a way to get rid of it if I want to keep this space at a constant temperature. In this example, I'm trying to keep it at a constant 75 degrees, but it's 90 degrees outside. So One way that I transfer heat is with transmission. This is basically, for the most part, conduction. So I have 90-degree air outside. It is warming up the 90-degree roof on top of my head over here. That's warming up all the materials that the roof is made out of, which is warming up the top of my ceiling, which is warming up the air up through my ceiling. Now, it doesn't happen instantaneously. It takes time for that heat to move its way through that assembly. The amount of time it takes to move through this roofing assembly or the transmission through the wall assembly, the amount of time it takes is a function of the insulation value of that assembly, the R value of it. So how good is my wall? What's it made out of? And not just the insulation, but any other materials that are in that wall. Is it brick? Is it, aluminum siding? What's slowing down the heat transfer through the wall? But that heat transfer through the wall is our transmission. Now I also have infiltration. What infiltration is air that's leaking into my building. So transmission is warming up the surfaces in order to warm up the inside of my space. Infiltration is I have 90-degree air that's leaking into my space through a hole somewhere, or and more likely many, many, many holes. Right, so I have to deal with that as well. I have to know how much infiltration there is and how I'm going to get rid of it. Believe it or not, infiltration is one of the harder things to figure out at the design point. If the building's small enough, you can put a blower door on there and actually measure it. But from a design standpoint, a lot of folks just guess at it, and it's really often overestimated considerably. But you got to do something. Our third main type of external heat gain is solar, right? So solar is our radiant energy. So that sun is shining, in this case, straight through the window, and it's going to go right through the glass. It's going to refract a little bit through the glass, but it's going to basically come through the glass, and it's going to hit an object. So in this case, the floor, a desk, the guy himself, right? And once it hits that guy, it's going to be converted to type of heat that he'll be able to feel. And that will add heat to our actual space as well. Just like I put insulation in the walls and attic to minimize that transmission gain, and I can caulk stuff to minimize the infiltration gain, there are ways I can minimize the solar gain. I can buy windows that are more reflective, that reject that solar energy. Although in the wintertime, I want to gain the energy, usually, and in the summertime, I usually want to reject it, depending on the type of space. I can also design awnings or overhangs on the outside of the window, because in the summertime, the sun is up fairly high in the sky. So if I had an awning right here where my little red dot is, that sun would hit the awning and it wouldn't go directly through the window. But in the wintertime, the sun is at a lower angle. It's kind of where my red dot is right now, and that would shine underneath the awning, and some of that would go in through my window and help warm my space up. So there are things I can do to design around that. You'll notice that older homes on the east, west, and south sides of the building, they will typically have awnings on there. If you're looking at stuff in the pre-air conditioning era, 1910, 20, 30, 1940s, they almost always had awnings on those buildings. And then when we started getting really common with air conditioning in the 60s, 70s, and 80s, they started designing those out of there and kind of forgot the right way to design a building, if you will. As you guys have questions, go ahead and type them in the chat box there, and I'll do my best to try to answer them as we go along here. So my building load, that is a combination of my internal gains, people, lights, and potentially equipment, and my external gains, transmission, infiltration, and solar. So I need to add all of those up to determine how much cooling capacity I'm going to need to cool this particular room. Right? So it's kind of a summary of all of those things. In the opposite season, when it's cooler outside, see if we can put this up a little better here. When it's cooler outside, I have heat loss. Sorry, I'm talking about gains there on the other side. I have heat loss in the wintertime or any time when it's cooler outside than it is inside. Right. So today it's obviously a snowy day. There's a snowman out there, so it's pretty cold outside. We'll just pretend it's like 10 degrees out or whatever, and it's 75 inside. So I'm still going to have that transmission happening between the building walls and the ceiling and attic. It's just going to be, the heat's going to be leaving now instead of coming. Heat always goes from hot thing to cold thing, like we talked about last week. So if it's 74 degrees outside, my heat will be moving from inside to outside, right? If it's 76, in our example on the screen here, it'll be moving from outside to inside, right? But if it's a 1 degree difference, it's not going to move very fast. The delta T between inside and outside is what really dictates the speed and quantity of heat that I can move in a given amount of time. So if it's 10 degrees outside versus 74 degrees outside, it's going to move heat out of my building much, much faster. So I still got the transmission losses. I have infiltration, right? Any air leaking in of that 0 or 10 degree air in the wintertime leaking in is going to be a penalty to me, and I'm going to have to heat that up. But there is one thing you'll notice that is missing from this discussion, and that is the solar, right? You would think logically that the solar gain would be a benefit to me in the wintertime. I would get that free heat. And in reality, that is true. I do get that free heat in the wintertime from the sun. However, the time that I'm designing the equipment for, the time of year is, whatever, January at some very late time, 2 a.m. or something like that, when it's the absolute coldest outside. And at that point in time, the sun is not up, right? So I don't get a credit for sun in terms of designing my system. Back on the summertime load, I got my worst time of heat is probably like 3 or 4 o'clock in the afternoon after the sun has been beating on my roof and walls for a long time. So the sun, the solar radiant energy, is part of my equation for that worst, hottest day of the year. But for my worst, coolest day of the year, the sun's not in the equation, so I don't take a credit for solar. Eli types in humidity loss a factor in the winter, humidity gain in the summer. That is true, Eli, if I have infiltration air, right? So I don't have any humidity gain or loss with transmission or solar, but the infiltration that I have coming into the building, that air could be drier or moister than whatever I have inside my space, and that will be a factor as well. So it's especially noticeable in the summertime when I have humid air, or actually it's really most noticeable on a day like today where it's not summer. I'm in the cooling mode, right? But it's not like summer. It's only like 80 some degrees, but it's still kind of humid out like it is today. That's when I really have the penalty of bringing in that moist air through my infiltration or through my ventilation system. It's a good point, Eli. All right, let's do quiz question number 6. I will populate that up right now. Maybe I will. Getting it. All right, quiz question number 6. What is which of the following indoor effects produce load in a building? Choose all that apply. So what indoor effects produce a load in the building? A, furniture, B, ventilation, C, people, D, lights. Choose more than one if you need to. If you guys have any questions that you want me to answer while you're answering the quiz questions, feel free to type them in the question chat box, and I'll try to pay attention to them here. All right, 71% of the people have answered, 81% have answered. I'm going to give it another 5 seconds, and then I'm going to close it. Okay, I'm going to share the results with you guys here. All right, so most people did pretty good. Most realized that furniture is not a heat source. I guess potentially if it was sitting outside in a truck and you brought it in and it had some embedded heat in it, but after a couple hours, it would never have any heat source again. The correct answers are C and D, which is people and lights. Those are our indoor effects that produce load in a building. Ventilation is not an indoor effect, obviously. It's an outdoor effect. It is air coming in from the outdoors. So for those of you that answered B, which is quite a few of you actually, that was an incorrect answer. The answers are C and D. All right, we'll go back to our presentation here. So let's talk about the different ways we can distribute the air in the building and then how we can treat the air. So I do need to have a fan typically to move air in the system. There are forms of strictly radiant heating and cooling. Those are fairly niche, and we're not going to focus on them today. We're going to focus on air-based systems because that is 98% of what's out there in the United States. So I need to have the ability to get air from the space, bring it to a piece of equipment, treat the air, which means heat it, cool it, humidify it or dehumidify it, and then deliver it back into the space, right? So some of the pieces that are going to be involved here. The first thing is I'm going to need some kind of fan. in order to move the air, right? I have to be able to draw the air from the room and then deliver it back into the room. So I need an air handler or a fan. I need ductwork to connect these systems. I could put a piece of equipment directly in the room with no ductwork, but in most cases, the equipment will be on the roof or in a mechanical room or in a basement. And that's how I'm going to locate the equipment. I'll be connecting it to the space with ductwork. And then I'm going to need to add the heating and cooling equipment inside, right? So you can see I got a coil and a filter there, and we're going to expand on those pieces in a bit here. I also need to have the right type of distribution. It doesn't make any sense for me to only have supply in the room. Like I said, I got to pull air back out of the room. So even though this drawing doesn't show the return on this particular drawing, I do need to have the return ducts. Ideally, in the perfect world, what I would do is if I was in the heating mode, I would supply air at the floor level, and I would return it back at the ceiling, because I would pull the hotter air off the ceiling and bring it back around. In the cooling mode, I would pull it off the floor and I would supply it from the ceiling. So residentially, what you'll end up, and that would require me to have two sets of duct, but I'm not going to do that for any realistic building. Residentially, what you're going to find is the vast majority of systems are going to have their supply and returns at the floor level. That's going to be the most common for two reasons. One, in residentially, I'm mostly in the heating mode, so I typically want to supply that heat from the floor level where the occupants are. But two, a lot of systems are basement located, so the ductwork is shortest if I do my supply and returns from the floor level. Commercial buildings, you'll mostly find the systems at the ceiling level. There's a couple different reasons for that. One, I am usually in the cooling mode in a decent-sized commercial building, and it's better for me to cool from the ceiling. So I typically do it that way. A lot of the equipment is roof-based, especially on 1- and 2-story buildings. So the duct runs are shortest if I locate the equipment at the diffusers at the roof. And then the third thing is, in commercial building spaces, they tend to get reorganized quite a bit as tenants move in and out, and it's easier to move stuff above a fake drop ceiling grid than it is in floor concrete. But in either case, whether I have floor-based systems or ceiling-based systems, commercially or residentially, I need to locate these diffusers correctly. I don't want two diffusers side by side blowing into each other. That doesn't make any sense. Ideally, what I'd want to do, let me get my little highlighter, is in a lot of commercial buildings in the perimeter zone, I'd like to put a linear slot diffuser in up here above the window and then blow air towards the glass and away from the glass and let it wash down the window, because the window is going to be my coldest surface in that space or my hottest surface in that space. So I want to kind of wash that window with some direct air blowing on it. Typically, I want the diffusers, whether they're at an exterior wall or an interior wall, I want them to throw all the way across the ceiling and then halfway down the wall. So across the ceiling, bounce, and then go halfway down the wall. That's typically how I want to select and space my diffusers in there. If it's a really big space and one diffuser is not going to throw all the way to the wall, I want that diffuser and the diffuser that are next to him to be able to both throw towards each other, basically collide, and then go halfway down into the space, down to the 4 or 5 foot level. So that's kind of how that typically goes down. Residentially, it is pretty good practice to have your supply air at the exterior also. So even though you got a floor-based system, I'll typically put the supply registers in front of the window to wash the window vertically up, and then I'll put the returns over on the interior walls typically. Right? I typically want to have the supplies and returns reasonably far from each other, so the air has to move through the space, which is what I really care about, in order to get back to the system. Angela asks if you could have a single duct system and then reverse the flow seasonally. I suppose you could do that. There's a couple things you'd have to do. One, you'd have to have the ability to have some diverting dampers down in your mechanical room to redirect the air to the supply and pull it from the return. That's going to take up a lot of space, so it's not very practical. The other thing you'd have to do is your return grills would really have to be selected as supply diffusers. Return grill could probably go either way. A supply diffuser is very directional and airflow specific, so you wouldn't want to use a return grill as a supply diffuser. It's not very practical to do it, though, just because of the amount of ductwork space you would need in order to reverse these airflows would not be realistic in most cases. Whatever air I want to supply to the space, I want to bring the same air from the space. How do I know how much air to bring into the space? That comes from my load calculation. We talked about before, I have to add up all my heat gains and heat losses and figure out what the worst case scenario is. Once I know the worst case scenario for this particular room, let's just say it's 1,000 CFM because that makes the math easy. So 1,000 cubic feet per minute I want to deliver into this space. I need to design my air handler, my supply duct, and my supply diffusers for 1,000 feet per minute. Then I want to get 1,000 feet per minute back out of that space. So I need to design my return grill and my return duct for approximately 1,000 feet per minute. Now I want to keep my space slightly positive, so maybe I'll only design the return for 900 or 950 or something like that. But essentially, it's basically going to be the same amount in that case. In many cases, I want to bring fresh air into the space. This is required in almost every municipality for commercial code, and nowadays it's required very commonly residentially. In the state of Illinois, it's required statewide residentially. For you guys in the other states, Minnesota, it's now statewide for you guys in 2015 finally. Well, your tightness level dictates your mechanical code kicks in, but that's another discussion. But in most cases, you need to bring fresh air in. So I might have to bring 1,000 CFM into this room, and then I might have 800 coming out of the space and 200 coming in the outside air intake or something like that. But between the return and outside air, it's got to add up to the same as the supply duct system. I do want to filter this air. I want to filter both the outside and return air streams. So I do want to have that air filter in there and change it regularly. The air filter there is there primarily to keep stuff from getting on my fan, my heat exchanger, and my DX cooling coil or chilled water cooling coil. It also can be used to protect the occupants with a little bit better air quality. For heating systems, I need to choose what type of mechanism I want to heat this air up with. Right, so there's several different choices I can choose from. Some are very common, some are much less common. Right, so I could put a steam coil in there, which means I have to have a boiler somewhere that's boiling water and making steam, and then through piping distribute that steam over to my coil, and then I run air over the coil to heat up that air with that hot steam coil. This is not done residentially at all anymore. I can't think of any applications in the past 15, 20 years I've seen that have had steam coils residentially. It is still done occasionally in commercial buildings, usually really old buildings that have not upgraded yet, or sometimes maybe in very large air handlers at a hospital where they have a lot of outside air and they have steam for other reasons anyway, those sorts of things. A more modern version of that, for the past 30, 40, 50 years is the hot water coil. I'm still using a boiler, but I'm not actually boiling the water to make steam. I'm just making it really, really hot, and I call it a boiler. Typically 180-degree water is very common. The boiler will make that, and I will use piping system and pumps to distribute the water to my coil, and then I'll run the hot air over the coil to heat the air up. So that's a fairly common mechanism. It's more common commercially, large commercial buildings, than it is in light commercial or residential, but you can see it in all three building types. I could also use an electric heating coil, which we'll talk about that in a little bit here as well. I could have a heat pump, or I could have a direct fired or indirect fired gas burner. All right, so there's a picture of my steam coil. This would typically be in a large air handler. And the steam coil and a hot water coil look the same. They're basically the same thing. So I would be just, depending on whether I'm bringing steam or hot water to the coil and running air over it. Electric resistance heating is an interesting way to heat. It is probably the least costly from a first cost standpoint. The heaters are very light. They don't take up very much space. I don't have to run piping. I don't have to run gas lines. I just run electricity to it, which I was already running anyway for the fan, so I just run a little bit higher amperage, a little bit thicker gauge wire, etc. However, it's not typically the most energy efficient way to heat a space. So this is what electric heating coil looks like, and even if you've never seen one before, it probably looks fairly familiar to you because you probably have the exact same thing inside your toaster at home, right? That's what an electric heating coil is. It's the coil that's inside your toaster. It's just much, much larger. So all electrical wires have resistance associated with them. As I flow electricity through there, the wire itself has an impedance and resistance, and that resistance has a byproduct of waste heat. Now, if I have a 1,000-foot wire and it's going 1,000 feet, it's all stretched out, that little bit of waste heat, it doesn't really amount to anything because it's being distributed over 1,000 feet of distance. But if I jam all that wire into one space and I coil it up really, really tight, and I run very high amperage electrical situation through it, it generates quite a bit of heat, and I'm able to heat the air substantially with electric resistance heating. So that's one mechanism I could use to heat the air. I'm going to come back to the heat pump here in a second. I'm going to skip ahead for just 1 second. Another type I have would be gas-fired heat, or fuel-based heat. Typically that means natural gas in our market. In more rural markets that will mean propane, because they don't have natural gas distribution lines, or oil, because they don't have natural gas distribution lines either. So the way this guy works, this guy is basically your gas furnace at home or your gas-fired rooftop unit. So I bring combustion air into the heat exchanger. Typically, ideally, this would come from the outdoors. Sometimes it is the combustion air is stolen from the space, which means air has to leak in somewhere else to make it back up. So ideally, I'd want to have a direct pipe from outside to inside, bringing my fresh air into the heat exchanger. So I bring that air in, and I'm going to use that air along with my gas flow and an ignition source in order to burn that fuel. It's going to go through typically 2 heat exchangers. On less efficient equipment, it'll be a single heat exchanger, but on more efficient, 90% and up, there's going to be 2 heat exchangers involved, a primary and a secondary. There doesn't have to be 2. It could be one really large one, but because the cost to manufacture the condensing side of the heat exchanger is high, because it needs to be made out of a non-ferrous metal, like stainless steel, aluminum, titanium if you can afford it. I don't want to make the whole heat exchanger out of that. So I'll typically make the regular primary heat exchanger out of steel or aluminized steel, and I'll make the secondary out of stainless steel or something like that. So that gas combusts, and I have my exhaust goes through this heat exchanger, right? The way my red mouse is going, and then the air from my space is coming up through the furnace assembly this way. Right, so he's seeing the coolest fuel gases first. That heats some of the air up. Then he's coming up further and he sees the hottest fuel gases, and then he gets delivered to the space. My fuel gases, after they make their way through both heat exchangers, then vent out to the exterior, and that does need to be vented and ducted all the way to the outside of the building, or to some unoccupied, unconditioned type scenario, like let's just say the outside of the building, because there are ways to vent it into an attic, but that's just stupid. So that's my fuel-based heating source. So the thing is, my fuel-based heating sources, which are furnaces and the boilers themselves, typically they're around 80 to 82% efficient. If you get a condensing one like I'm showing here, you're up above 90% efficient. It's very common and affordable to get 95% furnaces and boilers, and on the market you can find 97, 98% efficient furnaces and boilers. That's about the top end. 98% efficient means that of all this gas that I brought into this flame right here, 98% of that heat energy went into the air going into my space. 2% of the heat energy actually exhausted out of the building, right? So I'm 98% efficient, or 97 or 95 or whatever it is. That's about as best I can do on a combustion source, unless you want to breathe exhaust fumes. Then I could be a direct fired piece of equipment and you could be 100% efficient. That's only common in really leaky buildings like warehouses and stuff like that. Now, my other heating sources, right, for example, I'll go back a little bit here, my electric resistance heating, that's basically 100% efficient, right? Every kilowatt hour I buy from the electric utility gets converted into usable heat. Now, there is it could get a little bit of an orangish glow to it, so there might be some light output, if you will. So maybe you could say that it's 99.999%. But I would argue that eventually that light will land somewhere and heat that surface up. So it's basically 100% efficient for electric heat. So electric heat, in all cases, is always, always, always more efficient than the best gas furnace or gas boiler that you can buy. But that doesn't mean it's less expensive to run. It just means it's more efficient. Whether it's less expensive or not depends on your utility costs. So if you're here where I'm sitting right now in the Nicor gas territory, Nicor gas is fairly inexpensive. So the gas furnace and gas boiler typically always beat the electric resistance heating in terms of energy cost, but electric resistance heating is actually more efficient. Before we talk about heat pumps here, let me just see some of these questions here. I'm not sure of Eli's question about the hot water coils. Sal asks, if you bring outside air during the winter, is there a chance the evaporator coil on a standard AC unit could freeze? If so, what's a common way to prevent this? All right, so that's an interesting question, Sal, or Salvador. I guess it is potentially possible you could bring enough air in for the coil to freeze, but the refrigerant inside the coil is not going to freeze. So there's not really any concern about refrigerant busting a coil or something like that. You couldn't get the outside air cold enough to freeze the refrigerant. If you have a lot of moisture coming in and it's really cold, I could freeze up the humidity, freeze the moisture onto the coil. That's possible, but the refrigerant itself will not freeze. Now, with that being said, if you don't have a DX-based system, DX means that I have an evaporator coil in the airstream with refrigerant running through it. If I don't have that and I have a chiller instead, where the chiller is making cold water and I'm bringing water to a coil inside my unit, that water could certainly freeze based on the outside air temperature. And if you're in cold climates, and cold climates pretty much means Atlanta and northward, you need to have a freeze stat in your air handler that detects if the air ever gets below, the air coming into the chilled water coil ever gets below about 37 degrees, I go into oh crap mode and I shut off the blower, I close all my outside air intake dampers, I open up all my chilled water and hot water valves to move as much water as possible if that were to happen. But on a DX refrigerant-based system, there is no risk of the refrigerant freezing and any damage being caused. All right. So electric resistance heating is always more efficient than gas-fired heating, but gas-fired heating in most climates is typically less expensive to operate. Now, let's talk about a heat pump, which is another way we can make heat in the space. So what a heat pump is, it is a refrigeration cycle that's generating heat. It's actually a reverse refrigeration cycle. So in order to understand how a heat pump works, we first have to talk a little bit about how a standard air conditioner works. So on the top here, we're looking at a system here. Basically, it's a system that's in your house. I got a furnace or fan coil that's sucking air from my house, blowing it across my coil, and delivering it back to my space nice and cool for me. I have that coil in there connected to the outdoor unit with refrigerant line sets. So the first thing to understand is that we're not making the air cold. I mean, we are, but that's not really what we're doing. What we're doing is we're extracting the heat out of the air, right? I'm moving the heat out of the air and I'm dumping it outside into your yard, right? So you're bringing, 75, 80 degree air into this system. I'm extracting the heat out of it, which means you're getting 55 degrees coming out back into your house. And I'm taking that heat out, I'm running it through the refrigerant lines, and I'm dumping it to the outside. Now, I know I said before that heat always goes from hot thing to cold thing, and that's true. But with the refrigeration cycle, I'm able to kind of play the game here a little bit, and I'll explain to you how it works. But in this case, I'm actually able to move the heat from the hot thing, which is your house, and dump it into your yard, which is an even hotter thing, right? It's 75 in my house, 95 outside, and I'm able to move the heat from inside to outside. And refrigeration and pressure is why that works, and I'm going to go through that with you. But for right now, just know that we suck heat out of your air and we dump it into your yard. And we're going from the cooler room and dumping it to the hotter outside. So what a heat pump does is a heat pump reverses the responsibilities of the evaporator and the condenser coils. So literally the coil inside my house, which used to be my evaporator coil, now it's my condenser coil. And outside, my condenser coil is now my evaporator coil. It's like I took your furnace and your air conditioner, and I swapped them, and I put the furnace outside and the air conditioner inside, and then I ran it, right? Well, it's too hard to physically move them, so I have a reversing valve, like I'm highlighting over here with my red highlighter mouse, and I reverse their flow of refrigerant instead of actually picking up the unit and bringing it inside. So then what happens in the wintertime down in the bottom, what I do then is I extract heat from the outside air, and I deliver it through the refrigeration cycle to my indoor coil, and I dump the heat into your house, right? So just like in the summer, I can move heat from the 75 cool room and dump it in the hot outside. In the wintertime, I can move heat from the 30 degree cool outside and dump it into the warmer inside, right? That's how that guy basically works. It's an air conditioner that's literally running backwards. That doesn't mean the compressor runs backwards. It means I've temporarily repiped it with the reversing valve to make everything flow backwards. Now, the interesting about a heat pump is a heat pump, usually I ask a class how efficient it is just to see the guesses, but since you guys are all online, I won't do it that way. But usually when I ask folks, they'll say, well, it's less efficient than a furnace, that's for sure. Or they'll say, well, it's probably the same as electric heat. It's probably 100% efficient because it can't be anything more than 100. In reality, a heat pump, depending on the outdoor air temperature and the design of the heat pump, is typically between 200 and about 450% efficient. That means for every kilowatt hour of energy that I buy from electric utility, I'm getting 2, 3, 400 kilowatt hours of energy out of that thing, right? For every 100 I buy, I get 2, 3, 400 out. I'm getting 2, 3, 4 times as much out of it, right? The reason is that with a gas furnace or a gas boiler, I'm burning a fuel to make heat. With the electric resistance, I'm sort of kind of burning a fuel, electricity, to make heat there too. What I'm doing with the heat pump is I'm not burning any fuel here. All I'm doing is I'm not paying to make the heat. I'm just paying to move it. I don't have to make the heat like I do with your furnace. I just have to pay to move it. I got to pay to pump it from outside to inside. The actual heat comes from the air outside. And make no mistake, there's always heat outside unless you get down to absolute zero, which is like whatever, like not negative 273 degrees Celsius, right? If that happens, we're all dead anyway, so it doesn't matter. But there's always heat outside. Now, the colder it is, the harder it is to get the heat out from outside and pump it to the inside. So I have to have bigger surface areas of coil, or I have to have more fan airflow or something like that to continue to get more heat. But that's how a heat pump works. It runs the refrigeration cycle backwards. And we're talking more about the refrigeration cycle today as well. Just know that the heat pump is the absolute, positively most efficient way you could possibly heat a building. Now, once again, that doesn't mean it's the least expensive. Natural gas is super inexpensive here in the Midwest. So if you have natural gas available, it's probably the least expensive way to heat your building or your house. Now, if you're on propane or oil or all electric, now a heat pump can really pay back because it's probably going to be the least expensive choice to you if natural gas is not available. All right, let's do quiz question number 7 here. We can't do quiz question number 7 because I never talked about that a few slides back. So I'm going to do that, and you guys are going to basically get an easy question then. So just pay attention, I guess. Actually, I talked about it last week, but I'll talk about it again just to be clear. When I have an overhead heating system, ASHRAE handbook, as well as ASHRAE standard 62.1, dictates to me a maximum temperature that I can deliver for an overhead heating system. That temperature is 15 degrees above the space temperature. So if I have a 75-degree room, I am not allowed to deliver more than 90-degree discharge air. If I have a 70-degree room, then my maximum is 85-degree discharge air. The reason for that is if the air is too hot on an overhead heating system, instead of the diffuser being able to throw it across and halfway down the wall and into the space, instead that air just hugs up at the ceiling. The velocity of the air is not enough to overcome the natural buoyancy of the hot air to stay up, right? Because hot air rises. So if it's more than 15 degrees between discharge air of the diffuser and space temperature, the air will hug up here at the ceiling. And I'll end up with a stratified room. I'll end up with, 100, 110 degree air up at the ceiling, and it's cooling down into 90, 80, 85. And I'll eventually have 72 at the thermostat on the wall because the thermostat's always happy. And at the floor down here, I'll have like 53 degrees, right? The thermostat's still good, but it's really hot at the ceiling, really cold at the floor. That tends to not allow the ventilation air to be delivered down to the space. So the ventilation codes, ASHRAE Standard 62 and IMC, penalize you, and those codes require you to bring in 25% more outdoor ventilation air if you don't follow certain rules, and one of those rules is no more than 15-degree discharge temperature above the space temperature. Other rules include how far you got to throw it across and down the wall, which I said was halfway down the wall, and I got an exterior, you got to throw it towards and away from the glass. If you follow those things, you don't have to take the penalty. I talked about that last week a little bit, but I didn't talk about it today. So in fairness to you guys, we need to cover that again. So it's fresh. Otherwise, I feel bad about giving you the quiz question. Right, so for our heating choices, I got hydronic coils, I have electric resistance heating, I have heat pumps, and I have fuel-based burning. All right, now let's do that quiz question. If you can't remember from 2 minutes ago, it's not my fault. All right, what is the maximum supply air temperature for overhead heating systems per ASHRAE 62.1 and other standards? Your choices are 90 degrees, 110 degrees, 140 degrees, 15 degrees above space temp, and 20 degrees above space temp. I'll look at some questions while you guys are answering that. Eli made a comment that You can use hot water coils to be supplemental to the heat pump systems. That is true. If you have heat pump systems that are not designed to carry the full load, which is very common because the heat pump also has to do the air conditioning work, and typically the air conditioning BTU requirement in many cases is lower than the heat pump BTU requirement on a very cold day. So we size it for the air conditioning mode, which means the heat pump can't do it all by himself when it's 0 or minus 10 out, or even 10 possibly, positive 10. So in that case, I can use hot water coils or electric resistance heating or gas burners or radiant floors or any other type of heating source I want to supplement that heat pump and get that heat pump fantastic energy savings most of the time, not necessarily all of the time. All right, I'm closing this poll question because 90% of you guys voted. Sadly, 4% of the people actually got it wrong, even though I just went back and read the answer to you guys all. But most of you obviously got it. It was 97% of you saying that 15 degrees above the space temperature is the limit per the ventilation code. Some of you guys, I understand why you said 90, because it's often assumed a 15-degree room, or excuse me, 75-degree room, and the 15 degrees would give you 90. But if you have a 72-degree room, then the answer is 87. If you have a 70-degree room, the answer is 85. So the correct answer is number D, 15 degrees above the space temperature. Ryan makes a comment, 62.1 does not dictate a maximum discharge temperature, only identifies a penalty is enforced if your discharge temperature is above threshold. So that threshold, I guess we'll need to bring it up since you're asking about it. Let me see if I can pull up the code real quick without having us too much of a time penalty here. Books, codes, 62.1. And let's see if we can find it relatively quickly. If anybody knows the section number offhand, go ahead and tell me because it'll be faster for me. But definitions. If we could just scroll through here, maybe. If I get to the table, then we can see it real quick. No, looking for the ventilation effectiveness. Maybe that's. All right, system ventilation efficiency. That's not the one we wanted. Oh, here we go, on top. So right here, I'm going to highlight it for you. Hopefully you guys can see it on my screen. Ceiling supply of warm air 15 degrees or more above space temperature and ceiling return. So if you have a supply system that supplies are on the ceiling and returns are on the ceiling, you are going to get a penalty for being more than 15 degrees above the space temperature. The penalty is you have to use a 0.8 for your ventilation effectiveness, which means you have to basically take a 25% penalty to make that back up. So hopefully that clarifies what you're saying. I see your point, Ryan. It doesn't say you can't do it. It just says that if you do it, you got to bring in 25% more outside air than the code tables otherwise said. Right? So if you're back here looking at your table saying, oh, I got to bring in this much outside air per the code, multiply that by 1.25, and that's how much you really have to bring in. So yeah, it doesn't prohibit you from having really hot air, but it penalizes you very severely. One more question here, and then we'll move on. Robert types in, why does the gas heat into a furnace coil serpentine downwards instead of up? Right. So in this example that I was talking about, I have an upflow situation, which means my air is where my red dot is down here. Hopefully you guys can see that red dot. My airflow is coming up through the heat exchanger this way and then being delivered to my space. But the heat exchanger is going counterflow to that, right? So my intake, where my fuel is the hottest right here at this blue flame, is the hottest here, and it's moving its way, serpentining through the heat exchanger that way, and it leaves the furnace at its coolest temperature. I want it to be a counterflow situation. This is not just for a gas heat exchanger, but this applies to a DX coil, a heat pump coil, a hot water coil. I almost always want the flow to be counterflow. Because what that means is that when my air comes in here, where my red dot is at, let's say it's 65 degree entering air into this heat exchanger, if he saw the hottest heat exchanger temperature first, he would warm up a certain amount, and then the rest of this heat exchanger surface area wouldn't be able to do anything because the air would already be warmer than the heat exchanger surface temperature. So what I want to happen is I want the coolest air to hit the coolest part of the heat exchanger first. Now, coolest part of the heat exchanger means it's whatever, 180 degrees or something, right? That's surface temperature. So I want that to do the work first, and then as that air is warmed up, now it's now it's 80, 90 degree air. It's getting warmed up. Now it's hitting the even hotter surface temperature of the heat exchanger. So I want the coldest air to hit the coldest part of the surface of the heat exchanger first, whether it's a hot water coil or whether it's a gas burner. So if I had a hot water coil with multiple rows, I would feed the hot water into the last row, and the return water would come back from the first row, the inlet row, if you will. That's the reason for that scenario. So hopefully that helps answers Robert's question. All right. So on the cooling side of the equation, removing heat from the space, we're going to focus on DX systems, right? So I got the same basic system here from the air handling standpoint, but I want to bring that warm air in and deliver it back to the space at a cooler temperature. So I got my heat exchanger surface area, which is typically, in most cases, copper coils, serpentine throughout, with fins on them. The job of those fins is to spread the heat out, right? So if you've ever seen, for you guys have never seen a coil, if you were just driving down the street and you see one of those green electrical transformer boxes sitting on the ground every so many blocks, they always have those protrusions sticking out of them. That's to give it more surface area so it can reject heat more. Heat transfer is very often a function of surface area in addition to air motion. So if I want to have more heat transfer, I need more surface area. So just serpentining a coil through here would only do a certain amount of heat transfer. Putting all these fins on here does the rest for me. Now, the amount of capacity that I'm going to be able to do is a function of how much surface area. So it's not just how many rows of coil that I have, but it's also going to be how closely are these fins spaced. Is there whatever 8 fins per inch? Is there 14 fins per inch? Obviously, if there's 14 per inch, I'm going to have more rows of fins that are jammed in there, and hence more surface area. The penalty to that is higher pressure drop, right? So I need to find that compromise of surface area and pressure drop penalty. My cooling system not only drops the temperature of the air like we were showing here, but it's also going to remove moisture from the air. Now, in order for it to remove the moisture and dehumidify the air, we have to get the air down to the dew point. If it doesn't get down to the dew point, the air is not going to condense on the coil, and hence the air is not going to drain off the coil. So it's kind of like you go outside in the morning and you see the dew on the grass. It only happens at times when the daytime was fairly humid and then the nighttime was fairly cool. So I got a lot of moisture there available to me, and I have this cool surface area, whether it's the windshield of my car or the grass or whatever. I can condense on that surface area. So same thing needs to happen here. I need to drop the temperature of the refrigerant and hence the air down below the dew point of the air. And once I'm below the dew point, then I will start bringing moisture out. The dew point means I cannot hold any more moisture. I'm 100% saturated. I'm at 100% relative humidity. If you give me one more drop of air, it's going to fall on the floor. I swear to God, don't give me another drop of air. Excuse me, I shouldn't have said it that way. So that's basically what that means. I'm at the dew point. I get one more drop of humid air coming in. It's going to condense and drip off onto the coil and then run its way down the coil into the drain pan and then drain away. So I need surface area to do that. I need fairly slow air motion to do that. So let's look at it, a little bit of an example here. So I have, in this case, a box of air that's going to come entering into my coil, right? I pulled it back from my space. It was 78 degree air. It was 72 grains of moisture. We talked a little bit about the psych chart the other day, last week, right? So 72 grains of moisture in a 78 degree day. I go and look at the psych chart for 78 degrees, and I see that at 78 degrees, I could hold 146 grains of moisture at 100% relative humidity. But I only have 72, right? So 72 divided by the maximum of 146 means that I have 49% relative humidity, right? So that's the idea there. My cooling coil, what he's going to want to do is take some of this entering air. In this case, I have 78 degree air at 100% relative humidity, 72 grains of moisture coming into my coil. And in this case, I'm leaving there at 55 degrees and 64 grains of moisture, which corresponds to a 49% relative humidity. That reduction in grains of moisture, 72 minus 64, 8 grains of moisture, that is an indicator of my latent cooling capacity. My sensible cooling capacity is 78 degrees minus 55 degrees, right? So I did 23 degrees of sensible cooling, and I did 8 grains of moisture removal on my latent cooling. Oops, sorry, I clicked on the wrong thing there. But unfortunately for us, every single air molecule that moves through the coil doesn't necessarily touch the coil, right? So it doesn't necessarily get cooled down and or dehumidified. Now, you're not going to put your temperature probe right on the exiting side of this coil and be able to see that. You know, when the air comes out, it's going to start mixing, and you get a combined 55-degree number, which means that in order to get 55 degree and 64 grains of moisture on average, I need to drop the air that hits the coil to something below 55, 64. I got to drop it below that, so once it mixes with the air that bypasses, I'm there. So let's talk about some of that bypassing air. So the air is a mixture. Like it's showing here, some of those air molecules are going to touch the surface area of a coil or a fin and get cooled and dehumidified. Some are going to skate through fairly, scot-free and not be touched at all. And those guys are going to mix back together. So in this case, I had to get my coil surface temperature down to about 53 degrees in order to get a mixed condition of 55 degrees. If I have less fins per inch or I have less rows of coil, in this case I have a 2-row coil. If I have less than that, I only had a 1-row coil, which would be really dumb. 2 rows is kind of dumb. Then I would have even a lower ratio, right? So that air that does not come in contact with the coil is our coil bypass air, and we have a coil bypass factor, which is very easily measured. I have 78-degree air, right? Which means I could potentially, if I did an awesome kick-ass job, I could have 25 degrees of work be done on that, but I only got it down to 55 degrees, which means I didn't get 2 degrees taken care of. So 2 divided by 25, right? For you math whizzes, it means 8% of it did not touch the coil. So I bypassed 8% of it. Hang on, my screen just... Oh, that freaked me out for a minute. My little GoToMeeting icon dropped off and I got freaked out. So I have 8% bypass, which means 92% of it came in contact with the air. If I want to lower the bypass factor, which means do a better job of cooling and dehumidifying this air, there are several things that I can do. One is I can reduce the coil air velocity. If I move the air through this coil slower, the air is going to not whip through there as quickly, so it's going to have a more chance to bounce around a little tiny bit, and bounce around meaning touching a little bit more of those fins. Right, so I can reduce the airflow through there, which gives me more time to have air in contact with the coil, and more likely that I'm going to be able to touch the surface area of the coil and hence reduce the temperature of that air. This is very often seen on residential systems. Anything that has an ECM or variable speed motor from a furnace standpoint typically has a dehumidification terminal on the furnace, and when we energize a dehumidification terminal from a dehumidistat, it tells that furnace, hey, put on cooling if you could at the lowest stages possible. But this time, though, run the blower as slow as we possibly can, because I want to really, really dehumidify and not do too much sensible cooling and really do my work on the latent side. So reducing the air velocity is one way to do it. We haven't done this very often commercially, not as often as we should. The VRF guys do a good job of it. Some of the air handler guys do a good job. But like the regular rooftop stuff, it's kind of been neglected. Just recently, in the past couple of years, it's been more common to do staged air volume on packaged rooftop units. And that allows me to have multiple speeds of fan on the rooftops, so I can reduce this airflow at lower load situations and do a better job of dehumidifying. So one way to reduce the coil bypass factor and dehumidify better is to reduce the air velocity. Another way is to space my tubes more closely, right? Or space my fins more closely. That'll do the same type of thing. The closer those things are, the less likely it is something could pass through. Just imagine I have this giant air handler and I only have 1 row of coil and there's only 2 fins on the entire coil. It's going to be pretty easy for me to stick my hand through there, right? Let alone and without touching anything, let alone the air going through there. But if I decide to add 3, 4, 5, 6 rows of coil and I decide to jam in, 9, 10, 11, 14 fins for every inch of coil, I'm going to be lucky if I can stick, a toothpick through there, let alone my arm. So I'm able to get much more surface area that way. So more rows of coil, spacing the rows more closely together, spacing the tubes more closely together, spacing the fins more closely together, and reducing airflow. All those things can contribute to me doing a better job of reducing my bypass factor, which improves my dehumidification ability. However, like I said, there is a penalty for airflow if I have too many fins per inch. So when we put that air into the room, we're not really making cold, dry air and trying to blow it on you. What we're trying to do is put cool, dry air into the space so it can absorb the heat and absorb the moisture from the space, right? So in this case, I'm delivering to you 55-degree air with 64 grains of moisture associated with it into your room. And that 55-degree air is absorbing the heat from the people, lights, solar, infiltration, transmission, etc. It's absorbing all that heat. Some of those heat sources, like infiltration and people, also have a latent component to them, right? So people are sweating and giving off moisture, and infiltration is leaking in potentially moist air from outside. So there's a sensible and latent factor to both of those. Other sources like lights, solar, and transmission are just straight sensible, right? So I'm trying to absorb the sensible and latent energy into this air. In this case, I'm able to do a certain amount of work on this air and then bring that air, as it absorbs my heat and moisture, then bring that air back into the air handling system. So I bring 78 degrees with 74 grains of moisture in, I cool it down to 55 and 64, bring it back into the space, let it absorb that energy again, cool it and dry it again, bring it back into the space, and just keep repeating that cycle over and over again. Let's see if we have any questions here. Okay, no questions, just a comment. All right, so that's our cooling cycle in the summer. We got the return air and outside air both coming in, getting cooled and dehumidified, delivered into the space, absorbing the heat, sensible and latent, bringing it back through. All right, let's look at question number 8 on the quiz questions here. We're doing pretty good on time here. All right, so the question is, which of the following will improve the dehumidification ability of the cooling system? A, reduce the air velocity. B, reduce compression capacity. C, increase evaporator coil surface area. D, A and B. Or E, all of the above. So we got about 65% of the people have responded. I'm going to give it 5 more seconds. All right, I'm going to go ahead and close it. Hopefully everybody had a chance to answer what they wanted. And I'll share the results with you. Most of you guys got it correct. 71% of you said all of the above, which is correct. We mentioned reducing the air velocity, right? The slower I move the air through there, the more time it has in contact with the coil, and hence it can dehumidify better because I have less bypass factor. I mentioned the reduction of compressor and capacity, right? We said when we have an active dehumidification mode, the thermostat asks the system to put on as little stages of cooling as possible and reduce the airflow. So reducing that compression capacity ends up giving me a much longer run cycle, which means I dehumidify more. I can increase the surface area of the coil. I can't do that actively. I have to design it that way. But give me more surface area, and I can also dehumidify better. So E, all of the above was the correct answer. All right, let's talk about the actual refrigeration cycle and how it actually makes the air cold, if you will, or removes the heat from it, more properly stated. All right, so let's talk about sensible and latent heat, and we're going to apply this to refrigeration. We'll start out with talking about water, though. All right, so in this case here, I got this pot of water sitting on my stove. I turn my flame on full bore. I start heating up the water from whatever, 50 degrees out of the tap. I'm heating it up. Life's good. It's getting hotter and hotter. It's 100, 150, 200, 210, 212 degrees, right? And everybody probably knows that at standard atmospheric pressure, water boils at 212 degrees, right? So once I get to 212, you'll start seeing the water boil. But what happens on the thermometer? Does the thermometer stay at 212? Does it go up to 213, 250? What does the thermometer do when I keep adding more and more heat? Right? I've been adding heat this whole time, and it's been making the water hotter and hotter and hotter. But then what happens when it starts boiling? Well, what happens is that 212 locks in. I get it up to 212 and it stops raising the temperature of the water. The water does not get any hotter, right? Now all of the heat that I'm adding to the water is not being used to heat the water. It's being used to boil the water. And boiling the water means I'm converting the state of the water. I'm changing it from a liquid to a gas vapor type state, right? It takes a huge, huge amount of energy to change the state of something from a liquid to a solid, solid to a liquid, liquid to gas, gas to liquid, in this case, liquid to gas. So all that heat I'm pumping into that water is no longer making the water warmer. It's locked in at 212. That's the maximum temperature it's going to be on an open top pot. It's locked in at 212. If I add any more heat, it's just used to boil the water and convert it into a vapor, right? Oops. Right, so that's our boiling there. That change of state is our latent heat capacity. So the total amount of heat that I'm adding via my gas burner is my sensible heat and my latent heat, right? Sensible heat was the increasing of my temperature is how I witnessed that, and the latent heat was witnessed by me boiling the water, changing the state of the water. The sensible heat and the latent heat combine to be my total heat. I want to do it that way with water first, so when we talk about it from a refrigeration standpoint, people got a better chance of understanding what we're talking about. Now, if I took that same pot of boiling water, and it's no longer an open top pot, it's a closed top pot, like a pressure cooker, and I lock it down, right, and I change the pressure, then some magical things can actually happen. Some of you guys may remember from, the old high school chemistry days, or even from the recent Deflategate, PV equals nRT, right? Pressure times volume equals some series of constants, and an R, times T, which is temperature. So the pressure times the volume equals the temperature. Not directly, but the constants make the units kind of work out. So if I were to raise the pressure, but I kept the volume locked in like I do on this pressure cooker, and I don't allow the volume to change, I lock it down, but I increase the pressure, right, then the temperature has to increase, even though I've not actually added any heat to it, right? Because pressure times volume equals temperature. If the volume's fixed, like it is on a pressure cooker pot, and I change the pressure, then the temperature has to change. If I raise the pressure, the temperature goes up. If I lower the pressure, temperature goes down, right? When I start thinking about a refrigeration system, my evaporator coil, my condenser coil, my compressor, my piping, all that's a closed system. It has no exposure to the atmosphere unless I have a leak, which hopefully I don't have. So it's a closed system, just like this pressure cooker. And if I were to change the pressure of it, and I increase the pressure of the refrigeration system, that's going to increase the increase the temperature of the refrigeration system as well. Right, so that's what we're going to kind of lead into here. So in order to start talking about refrigeration in terms of this boiling pot of water idea, we got to know when refrigerants boil. So water, we know, boils at 212 degrees. But when do various refrigerants boil, right? So our traditional, R22 refrigerant boils at negative 41 degrees. The more modern 410A boils at negative 62. 134A, which we use for chillers and stuff like that, as well as automotive, is negative 15 degrees. So regardless of what refrigerant we're talking about, these things boil at what I would call relatively cold temperatures, right? That's going to be important when we start talking about the change of state here. So the evaporator coil is my absorber of heat. So my 80-degree air coming in through my air handling system is going to go across that evaporator coil, and he's going to absorb heat, which means his temperature needs to be below 80 degrees in this case in order to absorb that heat. And the further below he is, the more he's going to absorb. So I want him down in the 50 degree range, 50, 53, 55 degrees, in order for him to absorb heat and make my 60-degree air in this particular example. So he absorbs heat. Why is my clicker not working? Clicker, cooperate. Okay, all right. Now my quick clicker's working. So coming into my evaporator coil, I'm going to have a TXV, and we'll talk about that in a little bit. He's going to meter the amount of refrigerant that comes in here, and it's going to come in as a gas and vapor mixture. And that gas and vapor is going to move its way in serpentine through my coil. In this case, it's only a 2-pass coil, but I usually have a lot more passes than that. And that guy, as he absorbs heat, right, that absorption of heat is going to cause my refrigerant vapor to start evaporating and becoming my gas to evaporate and become a full vapor, and then leave as a full vapor. So that heat is being used to change the state of energy of my particular fluid, which is refrigerant in this case. We're not going to talk about open refrigerant cycle today. We'll talk about a closed refrigerant cycle. This is my refrigeration cycle. This is used not only in refrigeration like supermarkets and stuff like that, right? But it's used in your house, in your rooftop unit, in your chiller, anything like that. So my condenser coil is sitting outside my yard and at my house. My evaporator coil is sitting above my furnace, right? Those guys are the yin and yang of each other. And by the way, the names evaporator and condenser, those come from what the refrigerant's doing inside there. They don't come from what the air is doing on the outside. The air is actually doing the opposite, right? So I said before, if I want to dehumidify the air, I got to blow it across the evaporator coil and let it condense out of the air, right? But then I call this the evaporator coil. It seems kind of weird from someone who thinks about things from an air side standpoint. But from a refrigeration standpoint, and by the way, all the HVAC systems evolved out of the refrigeration industry back in the day. From a refrigeration standpoint, the refrigerant is evaporating over here. And the outside, where he's rejecting heat, the refrigerant is condensing. So he absorbs all the refrigerant here. He moves to the compressor, rejects his heat outside, and condenses that gas, moves back his way back to the TXV. The evaporator and the condenser are yin and yang to each other. They're exact opposite. One evaporates the refrigerant, one condenses the refrigerant. The compressor and the TXV, thermostatic expansion valve, those guys are the yin and yang opposites of each other. The compressor has one main fundamental job in life. His job is solely to change the pressure of the refrigerant, to increase the pressure of the refrigerant. So it comes in at a certain pressure, he's going to step it up to a higher pressure. I said before, if I increase the pressure of refrigerant in a closed volume system like this, the temperature has to go up, right? Because PV equals nRT. So if I increase the pressure and the volume stays fixed, temperature has to go up. If temperature goes up, now when that refrigerant goes outside to the condenser coil, now the temperature it's hotter in the condenser coil than it is outside in your yard. So he has to give the heat up, right? That's how I'm able to move heat from the inside to outside, even though it's hotter outside. I change the pressure of the refrigerant, which increases his temperature, which now makes him hotter than the outdoors, so he can reject his heat at the condenser. And then that quote-unquote cool refrigerant can come back into my TXV. My TXV is my pressure regulator on the opposite side of the compressor. So if we look at it in a more data-driven fashion, I got my high side and my low side, right? My compressor is what changes the pressure. So he's right on the dotted line between low side and hot side. And the TXV, my metering device, is the yin and yang to that. TXV is our modern metering device. We used to use other fixed orifice type devices like pistons. Those are not very common at all anymore. TXV is pretty standard. In fact, TXVs have evolved into EXVs, electronic expansion valves, which do the same thing, but they're driven by microprocessors. So he's the opposite end of that. So I could literally draw a line through the refrigeration cycle between the TXV and the compressor. And by the way, this is an old recip compressor, which is why it looks like a hideous, ugly beast there. But I draw a line between those two. Everything on the bottom of my drawing right now is my low side pressure. Everything on the top side is my high side pressure. The low side pressure is going to absorb heat, in this case out of my airstream, and I'm going to then pump that through the suction line, which is in purple over here. The compressor is going to draw it through there and pump it, raise its pressure up, which will also raise its temperature. So I raised it from 68 psi to 260, which then raised its temperature from 40 degrees up to 120 degrees. And then when it's 120 degrees, I shove it into the condenser coil, and now because it's only 90 degrees or 95 in my yard, it seems like it's cooler in my yard, so I'm able to dump the heat into the yard outside. And then that cool refrigerant is brought back into the metering device, where the metering device then distributes it into my evaporator, where it can absorb more heat, and we can just go around this circle all day long. Compressor increases the pressure, which increases the temperature, and then rejects the heat because it's hotter than the outside, and then it comes back into the inside, and because it's now cool, only 40 degrees, it's able to absorb heat from that, 70-some degree airstream. That's your basic refrigeration cycle. It doesn't need to be more complicated than that. That's basically what we're doing. By the way, these particular temperatures and pressures on the screen right now are based on R22. We can do some examples here with R22 and 410A. We'll do them side by side so you can sort of see them. So in R22, my example was 40 degree 40 degree refrigerant and 68 psi entering the compressor. If it was an R410A system, I'd still have kind of that 40-degree temperature, but in order to have 40 degrees with R410A, because of the properties of R410A, I would have about 120 psi. That compressor raises those pressures. In the case of the R22, it raises it from 68 to 260, which raises its temperature from 40 to 120. In the case of 410A, in order to get from 40 to 120, I got to raise the pressure from 120 up to 419 in this case. All right. So all this compressor does is just boost the refrigeration pressure, and that inadvertently boosts the temperature, which makes it easy for me to dump heat outside. I probably should have mentioned some of the labeling of some of these lines. The inlet to the compressor, that is referred to as my suction line. Just think of the compressor as sucking the gas in, right? So that's my suction line, or sucking the liquid in, excuse me. The hot gas line is my discharge of the compressor. Since I'm raising the temperature, that refrigerant pipe is going to be warmer. I think I put it on here too, right? So my suction line goes from the evaporator to the compressor. The hot gas line goes from the compressor to the condenser, which in many cases, like in a rooftop or a residential condensing unit, that's a very short line and it's internal to the unit. And then my liquid line goes from my condensing unit back into my evaporator coil. All right. Clicking through. This is pretty much saying the same thing. It's just showing now we got the air on here as well. So I have 95-degree air in the room. I'm bringing in outside. I have 95-degree air outside. I'm bringing in refrigerant that is 120 degrees, right? So we had a minute ago, 120 degrees. So he's now warmer than the outside. So heat goes from hot to cold. So in this case, it goes from the condenser coil to the outdoor airstream. Sometimes you won't have condenser coils sitting outside on top of a building or outside in someone's yard. You may have a water-cooled condenser. So that, instead of having a refrigerant to air heat exchanger like your condensing unit has, it has a refrigerant to water heat exchanger. This allows me to dump heat from my compression cycle, from my condenser, into a water loop and then pump that water somewhere else. Now, in the old days, you used to have these pump and dump systems. You basically would, pump water out of a well and dump it somewhere. Or you would take city water, from city of Chicago or whatever at 50 degrees or whatever it is, and you would use that water and you would dump heat into it and then dump that down the drain. Those typically are not allowed anymore. The city water is definitely not allowed anymore, and pump and dump is very seldom allowed in any community from a well. So you're typically using a cooling tower in most of these cases now. So we will take cool 85-degree water from the cooling tower, and then I will dump heat into that from my refrigeration cycle, and that warms up that water to, in this case, 95 degrees. I send it back out to my cooling tower to cool it back down to 85. So I have an extra heat exchange process, not just this heat exchanger here, but I have the cooling tower doing the heat exchange outside, and in his case, he's using the evaporative effect to get a fairly efficient means of removing heat. The TXV, the thermostatic expansion valve, this is my metering device. This guy controls what goes into my evaporator. You saw probably a few drawings back that he has a sensing element on him. So that's this orange line here. He has a sensing element on him on the exiting side of the evaporator coil, so he can decide how much refrigerant to meter back into the evaporator coil. I want to make sure that I got all that refrigerant evaporated before it leaves and goes back towards the compressor. All right, so that's my complete cycle there. Now all I'm gonna do is I'm gonna take that cycle, I'm gonna stick one end of it into my airstream. That's the evaporator side. I'm gonna stick him into my airstream. The condenser side, I'm gonna stick into a piece of equipment outside and blow a fan across him as well. I blow fans across both the evaporator and condenser coil to speed up the heat transfer process. Otherwise, this would take forever, and I would need crazy massive size heat exchangers. All right, let's do quiz number 9. Let's check the time. We're doing okay on time. Quiz question number 9. The 4 basic components of a refrigeration cycle include, include A, evaporator, compressor, condenser, and TXV. B, condensing unit, evaporator, furnace, and thermostat. C, compressor, condenser, evaporator, and fan. D, TXV, EXV, piston, and fixed orifice. So what four components are basic to the mechanical refrigeration cycle? The refrigeration cycle is just one piece of our total HVAC system, but there's four major components in that piece. I'm going to go see what questions you guys might have typed in. Several comments, but no questions that need to be answered, I don't think. All right, 88% of you voted. I'll give it 5 more seconds. And I'm closing it. And 98% of you guys got it right. The four major components are the evaporator, compressor, condenser, and thermostatic expansion valve. Oops, sorry, let me close that down. All right, let's do quiz question number 10. All right, so number 10 is, and read all the answers before you answer. The compressor, A, pumps liquid refrigerant. B, lowers the pressure and temperature of refrigerant. C, draws refrigerant out of the condenser. Or D, raises the refrigerant pressure and temperature. So what is his true job in life? All right, 86% of you voted, so I'll give it another 5 seconds. And I will close the quiz. And 99% of you guys got it correct, so I probably made the question too easy. The correct answer is D, raises refrigerant temperature and pressure. That is his job in life. His whole goal is to get the temperature to be hotter in the condenser than it was in the evaporator, and the way he does that is by bumping up the pressure. And if the volume stays fixed, which it does in this case because it's a closed cycle, then there's nothing that the refrigerant can do other than raise his temperature because I bumped his pressure up. All right, so what other questions do you guys have for me? I think we are pretty complete here. Ended 5 minutes earlier than planned, but considering it's 3 hours long, 5 minutes off is not too bad. Does anybody have any other questions they want me to try to answer? I am going to, dang it, I thought I already did this, but maybe, let me see if I did it already. If not, I'll have to send you guys an email with it. I didn't do it. I will do it now, and I will send you guys a link on here of where it will be stored. But there is a guidebook that goes along with some of these training modules that I've been using. All right, this is what the book looks like. It's 72 pages and has lots of descriptions of some of the things that I was talking about, along with the pictures that I was using. That's where I got these pictures from to begin with. So I'm going to send that to you guys. If you stay online for the next 2-3 minutes, I'm going to post it online right now and send you a link through the chat box. If for some reason you got to log off or whatever, just send me an email later and I'll send you the link that way. Other than that, I'll wait for anybody to type any questions and I'll hang on for the next couple minutes here and I'll get that link set up as well.